test lab for imaging devices and manufacture of all kinds of test equipment for those devices. His special interest is objective measurement of key image quality parameters and the required algorithms. So he'll be talking today about contrast detection probability and presenting some implementation and use case issues. So please welcome Artman.
Okay, thank you. Welcome everyone to my talk, and I have the pleasure to be the last one in this session, so I can take advantage of my previous speaker. So Robin just pointed out the importance of P2020. That will be also part of me. Paul just had the statement, how do we know if something is really there? And that will also be part or incorporated in it. And Paola just said there's the reliability and that the environment is actually part of what we are doing in case of automotive. So a little bit about the background. There have been already a paper that was already mentioned earlier this morning by my co-author Mark Gysi, which was entitled The Detection Probability Performance, that was presented here, and this work also contributed or went into the IEEE P2020 initiative, where this is part of the image quality for machine vision subgroup. So you have already seen that, otherwise just can invite you again. There is this IEEE P2020 white paper available on the internet. You can just find it, and it's a reliable tool and can use that. So as it has been presented, and this is something new, and it is something that is well, not like SNR, which everyone knows or at least has an idea or understanding from. There is, of course, the high need to explain this and to provide information to everyone. And that's why I'm here as well. So I just want to take the chance to give it another perspective and also show how it was actually implemented, this CDP, or contrast detection probability. So first of all, what is it and why do we need that? We have seen similar things, especially also these images already earlier in the talk. And there are different reasons why the object contrast can change for an automotive camera. So in this case, this is something that is not really in the under control of the camera, but this is something where a camera system has to deal with. So there might be something like fog. So totally out of control, but actually something that might reduce the object contrast. Or like in the lower right, that is something where the windshield, or actually pollen dust on the windshield and sunlight cause a high flare, so that object contrast of the car in the tunnel is significantly reduced. And this is out of control of the camera. If you can see the windshield as part of the system, it is in there. But it is crucial. So we want to know, is my camera system actually capable to detect this car? Can I see the car on the right in the low contrast, or do I only have it on the other one? There are other effects in a camera system that might result into problems to lose contrast, and where you want to quantify that. So here's an example of HDR imaging. So luckily, the HDR tone rendering made it possible that you can see under these huge dynamic range issues, so a dark tunnel and a bright outside. So it's great that you can make this visible, but it's about detection. And what you see as well is that the white line on a dark road in the outside, it's the opposite. So it just inverted. So it's not a white line on a dark environment, it's now a dark line. So it just changed, and that is, of course, can be a problem, and this is something that you might want to know about. And especially if you have a detection algorithm that makes a serious decision for you in a car. And there are other issues for today's imagers. So as we've seen, so there are HDR scenes. So there are scenes that require a huge dynamic range. And there are images, or many imagers, that are capable to do these things by combining multiple exposures. And I borrowed this from the IEEE P2020 white paper. And what you see here is actually two different settings of the same sensor. So you can, just by setting, increase the dynamic range significantly. But what you also get is this kind of thing, so that you suddenly have what is considered as SNR drops. So when you switch from the dark image to the medium image or to the bright image, you go actually from the dark part of one image to or from the bright part of one image to the dark of the other. So you have a drop of the SNR. And it shows here in the image, so suddenly you have much more noise in a brighter environment than in the darker, which is totally, or is not expected. Or maybe your detection algorithm didn't expect that, and that can be a problem. Question is, if we now write it down as SNR drop, how much SNR do you need that your camera is still able to detect it? Very hard to tell. So of course people have some numbers in mind, but it's not really a measurement. So that's something where CDP comes into play, or wants to do work that you can say, okay, I need this specific CDP that my detection algorithm is actually capable to work with. And that comes, we also heard that earlier this morning, means that there is no easy number that tells you for all applications this is good. You have to do a use case defined, you have to define by use case the requirements and derive from that the KPIs that you have for your camera system. And this is definitely also true for the measurements that we're going to CDP, that we're going to see later. You have to work first from, okay, what do I actually want to do? What is this camera supposed to do? And then you can derive the numbers from that. Okay, so how do we get to the CDP? So, well, first of all, CDP is basically, it's based, and that's a fundamental thing, it's based on the probability density function. So let's say we have two distributions, and that are just the measurement digital values of gray patches. So you have distribution A and B, and they are somehow related to each other. And so that can, and from this relation to each other, we calculate the power density function from these two random variables, and then the CDP is calculated as the area under the PDF within a defined interval. And the interval and how you calculate, that's all up for the requirement design. So basically, if you have the two A and Bs and you want to get to the PDF, you could do a convolution of the two PDFs. It's not further calculated, discussed here. What we do is a random pairing thing. So basically, we have two distributions, and you randomly pick pixel from A, pixel from B, calculate a metric between these, and you get another distribution. And the distribution can be based on different calculations. So that can be this Weber contrast, Michelson contrast, or just the difference. So here in this example that is on the right, it's just calculated based on the difference. So that means you want to know, is there any difference between object A and object B? And it doesn't really matter if it's correct or not, it just needs to be, there must be some difference. Depends on your detection algorithm, what you want to do. So, and then you define the confidence interval, or what you, so based on your requirement, you say, I need this certain interval, my detection algorithm needs this so that it can work properly, and then the, basically the integral, or the area, what you see here in blue, that is what is the CDP. So I made a small animation to show that. So basically we have distribution A and B, and we have a fixed mean value, and we just increase the noise. And on the right side, you see the corresponding probability density function with the corners that we have, so with the confidence interval. And in this case, we calculate the Michelson contrast from A and B. And you see, the more noise I have, the wider, the higher the probability that you have a very high or very low Michelson contrast. And we say, okay, for our detection algorithm, we need to know that a certain contrast is also rendered as a specific contrast. So that's why I make a certain window, and then I calculate the CDP on that. And so the number gives me how likely is it that I'm within this area. So, but there can also be another approach where I just calculate the difference. And I make an open end. I just say, okay, I just want to know, does my camera create some kind of contrast? So is there a difference between A and B? And it can be higher than it actually is in reality. It doesn't really matter. I just want to make sure that there is some area. So what I made here, I just calculate the difference between A and B, and have a small lower end for my confidence, for the interval that I define, but I have an open higher end. So that means that if it's higher, it's fine. It shouldn't be lower than that. And that is also a way how you can define the CDP. So it's a CDP measurement, it's just a different usage of that and defining different areas there. Okay, so there have been already floating around in documents different graphs or plots of CDP, and that is important to see. So here in this two-dimensional plot that we have, the single point, that is the CDP for a given luminance and for a given contrast. So that's a single point, and what you just saw in the animation, that's a CDP calculation for a single point. And now we can also make that to a two-dimensional plot. So here we have on the x-axis, we plot its simulation data. On the x-axis, we have light energy or number of photons. And on the y-axis, we have our CDP. And we have three different lines here, each representing the CDP line, two-dimensional line or function for a given contrast. So that means that you have, for example, so this system, as it was calculated, needs 100 times more light to reach 100% CDP for a low contrast object compared to a high contrast object. So if you have an autonomous driving car, and your camera is supposed to detect road signs, you have a high contrast object. That might be, you can do that in lower light, but if you want to detect pedestrian or, like we have seen earlier, the black cat on the road, you have a low contrast object, so you need more light to do that. So then it depends on your application or on the use case if your camera is capable to do that and how you design it. And there is another extension to that. Then you go from the two-dimensional into the third dimension. So now we have luminance, contrast, and CDP as a three-dimensional plot. And the nice thing of that is, and I will show that later in some measurement results, if you have this three-dimensional thing and you say, okay, for my detection, I need a CDP of, like, let's say 60%, you could get a slice out of this three-dimensional thing, and then you have an area that is above 60 and an area that is below 60. And the larger the area above, the more you can detect. So you can think of kind of a dynamic range thing. So the higher the area, the more you can collect information. So some examples how this actually looks like in the measurement. I have to say, this is an implementation how we did it. We have seen in the talks about the P2020, there are also other implementations. And this shows this CDP is not one thing that is actually fixed. It's more of a concept that you can use is almost a concept. So what we did here is that we have a test machine where we have 6 light sources. Each of them features a test target like we see here on the right. So, and then the camera actually captures these targets. And the target has 36 patches, and we have 6 of them, and we can control the intensity of all 6 light sources. So that means that we have a lot of measurement points, we can create a lot of contrast and a lot of intensities. And so then from this, as we've seen before, we take A and B and calculate the CDP value from these patches. And as we have so many, so we have 6 times 36 patches, we can have a lot of different patch combinations for brightness, or for luminance, and for object contrast, so that we do this many, many times. And then you can come up with something like this. Yes, it looks a little bit noisy, but that's the way it is, as we're dealing with a real camera. So we have a CDP plot here for 50%, 35%, 25%, and 20% contrast, object contrast, plotted versus luminance on the x-axis and on the y-axis is CDP. So this is a lot of data, but if I step through that slowly, we can see, so this is a higher contrast, and the more I reduce the contrast, you see there are some drops in there. And this is actually what we want to see. So this is an automotive camera. So we see it's not that we have just a smooth function, it's dark, we have lower detection, and it's bright, we have higher. There are areas, because of multi-exposure things, where things are going on. And as we said before, there is the idea to or the way what you can do is to move that into a three-dimensional representation. So that is what you can do. So that is what you see here. So that basically it's taken that data, and now we have luminance, contrast, and CDP in one plot or in one cloud. And you see on the left, so you can roughly see the shape. So that means that low contrast or low luminance leads to a lower CDP, which is kind of intuitive for a camera engineer. But what you also see, and it's a little bit easier to see here on both plots, that you also have these drops. So that is what we have seen earlier in the SNR drop, but we also see that here in the CDP plot. And so this can be used to characterize a camera and to see how useful is it, or what are the limitations of my camera system. Can do the same thing with different settings of the camera, and with that derive different conclusions from that. How suitable is that camera system for my application? That is some of how we implemented that. There is also some theory work. How is CDP related to SNR? I refer to that as a paper. One reason it would be extensive here in the talk, and the other one, that's something that has been done by Mark Gieser, and I would be moving on very thin ice if I have to explain everything in detail. So that will be, or is, in the paper that will be available. Just to summarize that, so of course you have to make many assumptions if you want to, because in the CDP we have the distributions and for the SNR, as we have seen, it's mean value divided by standard deviation, but for the CDP we also take things like the distribution shape and these kind of things into account. So a lot of assumptions have to be made to make the link, but what we all know that CDP is non-linear linked to SNR, so it's not just like a correction factor on the SNR and you just go with SNR. Okay, to conclude from that, so CDP is a new KPI that is directly linked to the application and the use case, which is definitely what you want to have. And CDP can be used to describe the performance of many different components of the imaging chain. So how does my windshield influence the system performance? How do we express that with SNR? Well, with CDP, at least you could, the contrast component you could define. Or what is the CDP before and after tone mapping? So you use the same metric for different applications. And how much information, the midtones, do I lose due to multi-exposure HDR? Things that you can answer with CDP. But also CDP requires a well-defined requirement design. So how exactly do you calculate CDP? How you define the boundaries and these kind of things, it needs to be derived from that. So next steps for us at Image Engineering, for us as a team with Mark Gese, Bosch, and the IEEE P2020, is to define like best practice procedures, so actually to measure it. We need to provide guidelines for CDP calculation and the usage as KPI, because it's a complete new KPI. People need to be educated, need to learn what does it mean, what is good, what is bad, so that we hopefully in the future have this in specifications. We think that there's also work should go into the possibility to replace or enhance well-known things, not only like SNR, but also derived numbers from that, like dynamic range or sensitivity, which is like SNR 10. So these things, I think they can also be significantly improved if they are based on CDP rather than on SNR. And we could, that's something completely where we have to start with, that would be to extend the CDP calculation with another degree of freedom, and that would be the spatial frequency response. So then we would have a 4-dimensional plot, but that would be answering all the questions. But I think until we have that, we will have still a lot of discussion, maybe also here at the Electronic Imaging. So with that, I thank you very much for listening to me, and yeah, enjoy the conference.
Excellent, thank you, Uwe. Any questions from the audience? Paul here in front.
Thanks, that was really good. As you showed, there's an opportunity to get a lot of data out of this calculation, right? And I like your 3D plots, but I'm thinking as we go through the process in P2020 for the standard, you know, what would you imagine people would report out from their measurements? they going to report a 3D plot? Are they going to report a series of 2D plots?
So
Any thoughts on that?
So I could think of, I mean, it's depending again on the requirement design, but of course this is a lot of data, but you could now think of that you say, okay, everything that is, just to make it short, everything that is yellow is good, everything else is not good. So if you think about dynamic range measurement tries to define, okay, where do I have information and where do I not have information? And so here, if you could say everything that is yellow is considered as useful information, everything else is not, you can calculate an area or something, and with that, or integrate that somehow so that you come up with a number. The higher, the more information you have, based on contrast detection. So that would be, for example, like an information transfer or dynamic range kind of thing. That is what I would like to have. And of course, what we need at the end is to have like single numbers, because like in the automotive industry, where you have like OEM with tier 1, with tier 2, and so on, at the end it's some bullet point in the specification. So it needs to be, hey, this number needs to be higher than that. And for that, we need to come up with some numbers that are as meaningful as possible.
Thank you for the interesting talk. I have a question about what is the mathematical operator that is designated by the square brackets. I think that you mentioned that it could be autocorrelation, but it also could be subtraction. Now, if it is just a subtraction, you're subtracting signals, you're increasing also the shock noise. And so if the shock noise increases, there may be a difficulty with understanding what particular contrast might be.
So acoustically, I had difficulties to hear that, but like, was I understood correctly? So why we use here difference, or what we use as the calculation for that, or?
It's in your equation. You had an operator quantity around this.
It's that slide before. Yeah, so what you have there is an operator that is square brackets. It's on this slide.
No, it's not this one. It was around quantity S, wasn't it?
Yeah, okay, yeah. So this is borrowed from a site where it was defined to have like a 50% confidence interval. So you make your probability density function and say that you have a 50% confidence interval, so that you have plus minus a certain area, and with that you calculate the integral, or calculate the CDP.
So yeah, the continuation of my question is, since you suggested that you may be subtracting signal A from signal B, what happens to the noises? Because the shock noise in the pixel increases when you are subtracting signals.
Well, basically at the end, this is what we capture. So we have, like here, we have two patches that we capture, and we just take A and B as just the distribution that we create, pixel value distribution that we have from that. So if it's increased by shot noise, by read noise, or by any other occasion, it doesn't really matter. It's two distributions that we have. It's a distribution of pixel values that we have in A and in B. And then we calculate the ratio or the relation to these. So we do a random pairing. So we take a random pixel in A and either subtract or calculate the contrast with a random another pixel in B. And we do that many, many times. And that way you get a distribution of how likely is it that a certain difference occurs in my probability density function.
Okay. So, any other questions?
Yes, I have one.
We're reaching time now, so this is the last question.
Thank you for nice talk. Can you go back to a slide when you first show 3D picture of CDP?
The first measurement, or?
The first slide with the three-dimensional distribution of CDP. Like earlier. Yeah, this one.
This one.
So in this plot, it looks like when you increase the contrast, CDP is not increasing. Does that make sense? Because like later on you have a plot which makes more sense when you increase the contrast, CDP is increasing.
Well, so that is a three-dimensional plot and of a simulated here in this case. The other one was the measured one. But here, you have object contrast, so the contrast between A and B. You have the luminance, so the luminance as the mean value of A and B, of the mean luminance of that, and then the CDP in the Z direction.
So you're saying like that's correct that CDP should stay the same if you have improved the contrast?
Well, it's not that.
Or maybe it just like looks like not like.
Yeah, it doesn't show nicely here, but normally you have more of the other limitations. If you see that here in the real results, there you get the impression that low contrast or low luminance all lead to a lower CDP value, and high contrast, high luminance are to a high value, and that you have.
Yeah. Here I guess it increases, so which makes more sense. Thank you.
Okay, thank you very much, Uwe. Thank the speaker again, please. And with that, on behalf of the session co-chairs Stuart Perry and P2020, I'd like to close this session. Thank you very much. And I invite you